what to do, but anyway.
Okay.
Yeah. Because that's going to put me at 15 people, that's too many people. It's just is. I have to figure out how to handle it. Anyway, let's talk about the equation of radiative transfer, shall we? Yes, we shall. I hope you're as excited as I am, because I do love this. So, equation of radiative transfer. You've seen the version that only has absorption so far, absorption and scattering. Why? Let's put an emission too, because photons at the end as well. The equation of radiative transfer, as in studying how radiation varies within, say, a star, anything else for that matter, the transport of radiation. So, equation of radiative transfer. Okay, so we know that processes that take photons out of the beam, we said we're going to call them all absorption and include true absorption, actual absorption, and scattering. Well, we're going to say that processes that add photons to the beam, those are called emission. Well, that's reasonable. It's emitting photons and add them to the beam. So processes that add photons to the beam are called emission. No coughing.
Great.
Yeah, I'm not coughing.
Okay.
I'm a terrible person. All right. So, for pure emission, without absorption, then we'll say that di lambda, change in specific intensity in the beam, will be, we're going to say J sub lambda, this will be the emission coefficient, J sub lambda rho ds. So J sub lambda here is the emission coefficient. And its units are meters per second cubed per steradian. If you look at it, that's what the units are going to work out to be for that. So the idea here is, before we had a minus sign because we were removing photons from the beam, there's no minus sign here because we're adding photons to the beam. Also, before we had I lambda in there, we had di lambda was minus kappa lambda rho I lambda ds, and that's because with absorption and scattering, it's happening to photons that are already there, and the more photons that are there to be absorbed and scattered, the more will be absorbed and scattered. But here we're talking about the material emitting photons that weren't there already, and so there's no I lambda there this time. There's no particular reason to have a proportionality to I lambda, and so it's just di lambda is J lambda rho ds. And so if we combine both absorption and emission, then we have, for the grand total, so to speak, di lambda is what we had before, minus kappa lambda rho I lambda ds, and now we'll add in this emission term, plus J lambda rho ds. So there's the differential change in I lambda in all of its glory, losing photons with this term, adding photons with that term. but it's convenient to divide through by kappa lambda rho. Dividing by kappa lambda rho is there in that first term. And now defining what we call the source function. We're going to say that's capital S sub lambda defined to be the ratio of the emission coefficient to the absorption coefficient, J lambda over kappa lambda. Then we can get our equation in the form minus 1 over kappa lambda rho, because we divided through by kappa lambda rho, minus 1 over kappa lambda rho, di lambda ds, lambda ds, because we're also we're actually going to divide through by kappa lambda rho ds. I shouldn't say, I forgot to put that in my notes. Kappa lambda rho ds minus 1 over kappa lambda rho di lambda ds is equal to I lambda minus S lambda. So this gets a box around it because this is the vaunted equation of radiative transfer. The equation of radiative transfer. And sometimes we just call it the transfer equation because it's so familiar to us, or will be. So notice on the right-hand side here, we've got a term related to what's already in the beam, I lambda, and a term related to emission and absorption within the beam. And of course, this must mean that I lambda and S lambda have the same units as one. Hello back there.
I'm sorry I was late.
So you didn't want to be on the camera and showing up.
I didn't want to disturb others.
What's that?
I didn't want to disturb others.
That's very kind of you. Yes. All right. What questions do you have at this point? No questions. Okay. Is that like a referee symbol? Okay. Yeah. My wife jokes that she watches football for them to call holding. She enjoys the holding call. Holding, but she's like, oh, I'm done with ball holding now. Obviously a huge fan. Yes. Not many people watch a sport for the refs, but in any case. In thermodynamic equilibrium, we know what I lambda is. What do we call I lambda in thermodynamic equilibrium? The particular form of I lambda, the Planck function. Why, what symbol does it be that we use to symbolize it?
B lambda.
B lambda, yes. That's the symbol that it be. I lambda is equal to B lambda everywhere. So it must be, in that case, that di lambda ds is 0. It's not changing. If it's b lambda everywhere, if we're in a region of thermodynamic equilibrium, we know I lambda is constant equal to b lambda along the beam. So that must mean that di lambda ds is equal to 0. And for that to be the case, it must be that the right-hand side is equal to 0. So this says that that S lambda must be equal to B lambda in thermodynamic equilibrium, right? Because, I'll just, in case you're looking at it later, like what? So the right-hand side equals 0, and that's going to say that B lambda must equal, sorry, I'm going to put it the other way around. S lambda must equal B lambda in thermodynamic equilibrium. Does that make sense? See what I'm getting at there? Both sides have, one side 0, the other side 0. So I lambda equals S lambda, but in thermodynamic equilibrium, I lambda is B lambda. So therefore, S lambda and B lambda are equal in thermodynamic equilibrium. And important results. Now let's back out, not in thermal equilibrium. Not in thermal equilibrium, then if I lambda is greater than S lambda, if I lambda is greater than S lambda, then, let's see, if I lambda is greater than S lambda, is the right side positive or negative? Positive. So di lambda ds, is that positive or negative? There's a minus sign right there. So if this side's positive, di lambda ds must be negative because there's that minus sign right there. There's that minus sign there. So if I lambda is greater than S lambda, then di lambda ds must be less than 0, right? Because it's kappa lambda minus kappa lambda rho times I lambda minus S lambda. And so since I lambda minus S lambda is positive, then di lambda ds is negative. So if di lambda ds is less than 0, I lambda, is it increasing or decreasing as S increases along the beam? Because remember, S is the length along the path of the beam there in the direction the photons are traveling. So if di lambda ds is less than 0, what's happening to I lambda as we move along the beam? Is it getting bigger or getting smaller? It's getting smaller, right? So I lambda decreases as it approaches S lambda, because the smaller I lambda gets, the smaller I lambda minus S lambda gets, and so it will approach S lambda until, and in general it take an infinite distance to get there, but it will approach S lambda, and if it got to the point where they were equal, then it stops changing. So I lambda decreases as the beam progresses, getting closer and closer to S lambda. Make sense? What questions do you have? Let's flip it around. If I lambda is less than S lambda, then what am I going to say about di lambda ds in that case? Di lambda ds, which way I'm going to put the inequality this time? It's greater than 0. And so this time, I lambda increases as the beam progresses, comma, getting closer and closer to S lambda. In other words, as the beam progresses, it gets closer and closer to S lambda. I lambda gets closer and closer to S lambda. Now, that's in any region. So if you have a very large region where the source function is constant, any radiation traveling through that region, any beam of radiation gets closer and closer to sharing that S lambda. Its I lambda, I should say, the I lambda gets closer and closer to having that value of S lambda as the beam progresses. So, in other words, the photons in the beam become increasingly like those produced locally, because that's what S lambda is talking about. It's talking about, it's got the emission coefficient in it, which will have wavelength dependence that's characterizing the photons produced locally. So we can interpret what this is saying as, in other words, as the photons in the beam become increasingly like those produced locally. At wavelengths where the beam has more photons than are produced locally at that wavelength, well, absorption is going to damp those down. And at wavelengths where the beam has fewer photons than those produced locally, emission is going to pump those up. And so overall, you get a configuration where the radiation is becoming more and more like that produced locally as the beam progresses, because you're eliminating the outliers and adding more photon folks that are like the ones produced locally. In LTE, long-term evolution, like cell phones, right? No, not like cell phones. What does LTE stand for? In our context here, you know it, local thermodynamic equilibrium in local thermodynamic equilibrium. So if you don't remember that, write local thermodynamic, no, actually write local thermodynamic equilibrium next to LTE there. In LTE, where S lambda equals B lambda, in other words, if we can get away with the approximation of thermal equilibrium, we already know S lambda equals B lambda in thermal equilibrium. In LTE, where S lambda equals B lambda, we see that, right, so we've got local thermodynamic equilibrium subregion, and then we fire in some radiation from outside, and watch what happens to that beam of radiation as it progresses through the region. We see that I lambda tends to quote unquote thermalize, become more and more like the black body radiation that's being produced locally as it goes along. An example of this is in the sun. How hot is the sun's core? Do you remember, or at least got an estimate? No. It's like 15 million Kelvin there, about 16 million Kelvin. If you had to guess, what kind of, where's the peak of the spectrum there? What kind of radiation is made in the sun's core? It's so freaking hot. Is it mostly visible light? No. Is it mostly ultraviolet light? No. Is it mostly X-rays? Yes, it turns out. In the sun's core, it's mostly X-rays that's being produced. Now, it's making even more visible light than the surface is. Blackbody radiation gets brighter at every wavelength as the temperature increases. But it's the sun's core, it's the X-ray region of the spectrum that's the most strongly emitted of all. So the sun's core is emitting all kinds of X-rays. By the time you get to the surface, is the sun emitting a whole lot of X-rays? No, it's emitting visible and infrared light primarily. What happened? Those X-rays from the core thermalized as they moved outward through the cooler outer layers of the sun. So, this happens in the sun. As X-rays and gamma rays, because nuclear reactions produce gamma rays too. I don't think it's hot enough to be dominated by gamma rays thermally. I have gamma rays in my notes, but whatever. I'll just say, as X-rays and gamma rays, the shortest wavelengths of all, as X-rays and gamma rays from the core, degrade to visible photons streaming from the photosphere. So we go back to our equation of radiative transfer. Let's rewrite. So remember it was -1 over kappa lambda rho di lambda ds is equal to I lambda minus S lambda. But we've given this combination a name in the past. We said something was d something was minus kappa lambda rho ds. What was that something? D. How much philosophical depth can you sum in order to answer this question? Okay. Yes, I'm asking a deep question about, you could argue, optical phenomena here. What could it be whose differential is defined to be minus kappa lambda rho ds? What could it be? What sort of deep answer could you give me? Could you give me an answer with any kind of depth to it? No, apparently not. Nobody's thinking of optical depth. Okay, so, if you have to say the punchline, the joke just totally falls flat. All right, anyway, I'll survive. In terms of the optical depth, where we said that d tau lambda, remember that? D tau lambda is minus capital lambda rho ds, why, we can rewrite the transfer equation. As just di lambda d tau is I lambda minus s lambda. Di lambda d tau lambda is equal to I lambda minus s lambda, which gives it a nice particularly simple form, simply. Now, before we talked about the idea of a plane parallel atmosphere, and we might be looking at different angles to the vertical in that atmosphere. So we say here's the z-axis perpendicular to the top of the atmosphere, which is of course a bit mythical because atmospheres just fade away. Oh my gosh, no sneezing either. Top of atmosphere. Here's angle theta away from the vertical. So we can talk about the vertical optical depth. And I'm going to draw this arrow, this double arrow here, but realize that's not physical depth, it's optical depth. So it's kind of qualitatively a distance, but we want to have the optical depth that I'm really talking about there. So here's some lower point embedded within the star. We could talk about the vertical optical depth. In other words, if you look straight down through the surface to that point, at what optical depth does it lie along a straight down line? Versus if we look at a slant, where we would have the sort of slanted optical depth, like so. And so we'll say tau lambda is the optical depth at the angle we're actually looking through the surface at. There's our eye looking into the star's atmosphere. Ow, 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 it's so freaking bright. We better get our super sunglasses on. We're seeing to some depth, some optical depth along that line of sight. We can relate that to the vertical optical depth of that same location. So if it was real depth, well, then we've got ourselves a right triangle right here, and we would be able to say that the what of theta is adjacent over hypotenuse cosine. So if I want hypotenuse over adjacent, the what of theta tells me that. What's no, careful. That's not the inverse. It's not. It's careful. It's the reciprocal of the cosine, not the inverse function of the cosine, right? Yeah, the secant is the reciprocal of the cosine. So we can say that the vertical optical, sorry, the tau lambda is the vertical optical depth times the secant of the angle theta. And this is the relation we would hold if these were simple depths. But for every little segment along, just like we were talking about before, for every little segment along the path, for every little ds, here's ds, here is ds times the secant of theta. And so if you integrate those, all the kappa rho ds's, you get the same relation between optical depth and angle that you do with geometrical depth, true in meters depth below the surface and angle. So we can talk about the optical depth along the actual line of sight is the vertical optical depth times the secant of theta, that angle from the vertical into which we're looking through the atmosphere. So, makes sense, or what the hell am I talking about? What's your reaction? You find what I'm selling? Yes, question, or, yeah?
Why do we have who's like the actual optical depth?
So in other words, I want to talk about, I'm looking along some particular line of sight, what's the optical depth of that thing down there? And I want to relate it to, okay, what if I instead were looking straight down at that same point? And
The Y.
so yeah, I'm calling it a Z here, right? You can call it Y, whatever you want to call it, right? You know, why not if you wanted to call it Y? The point is I want to make a formula where you can just talk about the vertical optical depth, the straight down optical depth, and I can make a correction by just multiplying by the secant of theta if I want the optical depth along some other direction. That's really the point. Okay. What other questions do you have? So I want to write a more general result where I just got the secant theta in there to throw in. Otherwise, I'd want to know, why do I want to keep track of every single line of sight? And I can just say, times the secant of theta for the downwards one to get every line of sight. So we can say that cosine of theta times di lambda d tau b, d tau lambda vertical is equal to I lambda minus S lambda. So now I've written an equation where if I'm looking at some angle theta, there it is, the cosine of theta takes care of that. So in other words, yeah, tau lambda is tau lambda d sec theta, but of course it also says that tau lambda b is the cosine of theta times tau lambda, but it goes the other direction too. Put it another way, right? What we're saying here is 1 over d tau lambda is equal to the cosine of theta over d tau lambda vertical. I'm just asking for Kathleen to say, what the heck am I writing here? Yeah, that's right. Yes. You can see that. Cool. All right. So what are we going to do with this? Why, we're going to do great things. We're going to get this whole business of, we quote-unquote see to an optical depth of 2/3, all that stuff I've been promising so long. You've been like crying because we've never done it yet. We'll work out to fix all that. So, let's get rid of the lambda dependence. Let's talk about an overall sort of average, if you like, or integrated optical depth, and so forth. In other words, let's integrate overall wavelengths. Add up everything overall wavelengths. So we're going to define the integrated specific intensity. I is equal to an integral from 0 to infinity of I lambda d lambda. Just add it up overall wavelengths. Because for now, we don't want the mess of considering every individual wavelength here. And, naturally, we're also going to define an integrated source function. So that'll be the integral over all wavelengths, 0 to infinity of S sub lambda d lambda. And the other thing we'll do is replace kappa lambda with the Rosalind mean opacity. Kappa bar. So that we have a so-called gray atmosphere. So why would we call that a gray atmosphere? Well, normally the opacity depends on wavelength. It's different at different wavelengths. And so if I were to hold up a blue filter, where is it transparent versus opaque? If I hold up a blue filter, you can see my face all blue through it. Does it have high opacity or low opacity at blue wavelengths? Opacity reflects how hard it is for the light to get through. So if you see my face through it, if I were a blue filter, here I am, I'm looking blue here, and it's not because I'm sad, it's because I've got this blue filter in front of me. Is that filter is the opacity high or low at blue wavelengths for that filter? Low, because light is getting through at blue wavelengths, and it's high at every other wavelength. That's why it transmits blue and essentially nothing else. So that blue filter has a low opacity at blue wavelengths and a high opacity at other wavelengths. But if I just held up what we call a neutral density filter, which you can buy for cameras and stuff like that, if I just held up something where it just made me look dimmer, but it didn't change my color, why, what color would that filter look like if I held it up to the wall? If I held up a filter in front of me, I still look like me. All the colors are there. It's kind of letting everything, it's blocking and letting things through equally. So it's got the same opacity at every wavelength. And now I hold it up to a white wall. What does it look like? It's gray. That's why we say a gray atmosphere. In other words, we're basically getting rid of thinking about different opacities at different wavelengths. We're just thinking of it as, it just blocks wavelengths equally no matter what. That's why we call it a gray atmosphere, quote unquote. Because kappa bar has no wavelength dependence. We've averaged it out. A filter like that would look gray if you put it in front of a white wall. So that's why we call it a gray atmosphere. It's all just hazy. And that'll be convenient because then there will be a unique correspondence between a unique wavelength-independent correspondence between geometrical depth and vertical optical depth. Geometrical depth means how many actual meters, kilometers, whatever it is below the surface. And vertical optical depth. We have to say vertical optical depth because the optical depth depends on the angle theta, whereas vertical optical depth, it's understood, that's the looking straight down theta equals 0 optical depth. So there would be a unique correspondence between geometrical depth and vertical optical depth. That's to simplify things. And having done that, we can write our equation without the lambda subscripts everywhere. So then we get to say, then cosine theta, again to account for you might be looking at some other angle besides straight down, cosine theta di d tau, just plain v, vertical optical depth, is equal to I minus s. No more pesky lambdas everywhere. Well, now let's get rid of this pesky business of looking at different angles. 2, 4, 6, 8. It's now time to integrate over solid angle. So, integrate over solid angle. Integrate over solid angle. And that'll say that d tau v of the integral over solid angle, I'll just say sphere. I'm integrating over the whole sphere here. Meaning all directions, in other words. If I'm integrating over solid angle for the sphere, that's code for I'm just integrating over all directions. Bring that cos theta inside to the integral because we're integrating, so it has, and it's the integral, right? It's going to be an angle over theta and phi in polar coordinates. So it'll be I cos theta d omega, that's the integral of the left-hand side of the equation over solid angle. Again, cosine theta has to stay inside the integral because remember that if I actually wanted to carry this out, I'm not going to have to right here, but what is d omega in spherical coordinates? If we take the z-axis upwards here, then do you remember what's d omega in spherical coordinates?
R side.
Get rid of the r because it's like dA over r squared gets rid of the r. So get rid of that part. So it's just d omega equals Sine theta d theta d phi, yes, which we're about to say. Sine theta d theta d phi, right? Now again, I'm not actually going to do this right here, but if I were carrying out the integral, if I wrote the limits, just to be sure you all remember, right? Why phi goes between what limits? 0 and 2 pi, and theta goes between 0 and pi, right? 0 and pi. So those would be the limits if I were actually carrying it out, but I don't need to here. On the other side, then we'll have the integral over the sphere of I d omega minus, now the source function is something that should be isotropic. There's no particular reason that material, except under bizarre circumstances, there's no reason for the source function to depend on the direction. The photons are just happily emitted and absorbed equally in every direction by the material that the beams are traveling through. So I can pull S out of the integration and just integrate over d omega for the whole sphere. Now, if I integrate over solid angle for the whole sphere, we get the number of steradians in a sphere. Are you going to make me super happy by telling me how many steradians in a sphere? 4 pi, right. So, I'm so happy about that. Yes. So that is 4 pi. That's 4 pi. And this beast right here, if you look through the notes, this is 4 pi times the mean intensity. If you look back, when we integrated I over solid angle, then that's 4 pi times the mean intensity, because the mean intensity is defined to be integrate I over solid angle divided by add up all solid angle, right? So it's just I I d omega integrated divided by 4 pi. So therefore, the integral of I over the sphere is by definition 4 pi times the mean intensity. And another thing that we can review is that this beast right here is the radiation pressure. That turns out to be the radiation pressure. So again, you might have to look that up as a reminder, but trust me, that's the radiation pressure. And that's kidding, it's not P. That's not a P, that's not a P. The flux, that's what I know. It's the net flux, it's the flux. It's the net flux of the radiation. I did that on purpose to see if you'd correct me, and nobody did. I'm just so disappointed. And meanwhile, I've got a bridge in Brooklyn that I'd like to sell you to. No, I just messed up. Okay, so, all right. So in other words, what we've discovered is that the derivative of the radiative flux with respect to vertical optical depth is 4 pi times the difference between the mean intensity and the source function. And again, these are integrated over wavelength. So this is so important that it gets a box and it gets called equation 1, because we're going to want to refer back to it. What questions do you have? So, one might be, where are we going with this? And this is one of these things, well, trust me, we have a destination in mind. You just don't know it yet. But there's like, here, everybody, come along with me. Come along with me. And we'll get to the end, and we'll open the door. Right, we're just undergo. Right, so it's one of these deals here. We're just walking through the forest here. What will we find? What will we find? You'll have to find it watching the video. It's okay. All right. Let's see how much more precious. We still have 1 minute and 40 seconds of precious education before the break. So, moment by moment here. Remember that we talked about moments of the radiation field where you multiply by powers of mu equals cosine theta. Why, let's do that here. Let's multiply now by cosine theta. Right? So this is, by the way, we call this the gray atmosphere transfer equation. And I guess I'll give you a little historical context here is, now we can make detailed solutions of the transfer equation on a computer. It's great. We've got fast computers, et cetera, et cetera. Believe it or not, when people were first really kind of studying this in depth in like the early 1900s, they didn't have super fast computers available to do all sort of thing. And so they needed to make approximations to kind of get anywhere. And that's what we're doing. But it's still worth doing, even though we can do things on computers now, because you get insight from these approximations that you wouldn't readily get just from the computer without detailed studies of the outputs and stuff like that. So that's part of our motivation here too. Okay, 10 precious seconds left where I mentioned, if you haven't checked your email, do so, because I put a message in Blackboard that kind of like, oh, hint, here's what one of the questions on the exam is going to be. And there's nothing stopping you from practicing it beforehand. I wonder, could I reproduce all those figures in mathematical myself? Yeah, just say. I mean, I'll guide you through, in the question or whatever. I'll remind you what the plot function looks like and stuff like that. The more ready you are to quickly use mathematics to do it, the better off you'll be. All right. Break time! There we can go. Hey, you sit in the front. And it'd be like this miracle. It's like, wow. Anushka materialized. That's a claim that's made, but nobody's ever proven that beyond any doubt that that's what's going on in the brain. There's various hypotheses. So if you see anything that says, oh, it's caused by this, we're not sure. Okay. So first of all, JKLOL, that's not the gray atmosphere transfer equation. This is the gray atmosphere transfer equation. I mean, that's, basically equivalent to it, or at least it's derived from it. But this is the raw gray atmosphere transfer equation right there. JKLLL. I was just kidding when I said that was it. And now we're going to multiply the gray atmosphere transfer equation by cosine theta and integrate over a solid angle. No. We're hungry for knowledge. And now multiply the gray atmosphere transfer equation by cos theta and go away from the vertical and integrate over solid angle. And so, by the way, kind of the idea here then is we're somewhere in the star and we're looking at the radiation and we're at different depths and so forth. And so when I say cos theta, right, keep in mind I am talking about angle away from the vertical. That's what cos theta represents. So letting the direction straight up to the surface be the z-axis. 2, 4, 6, 8, multiplied by cosine theta and integrate. So we get d tau vertical of, now this time we're going to multiply by another factor of cosine theta. So it's going to be I cos squared theta d omega. And then on the right hand side, I cos theta d omega, and I'm just going to stop putting sphere underneath all the integrals, that's understood. I cos theta d omega minus s can still come out, because again, there's no reason for the source function to depend on direction. So s integral of cos theta d omega but from earlier, right, you can dig this out of your notes, and it's the kind of thing I'd have to dig it out to. I don't necessarily remember all these little details like this. I forgot to get another piece of chalk. At some point I'm going to grade another piece of chalk, because I can't deal with short chalk. Anyway, little ring there. So, but from earlier again, it turns out that the integral of I cosine squared theta d omega was c times the radiation pressure, and the integral of cos theta d omega is, if you do that substitution we've done of mu equals cos theta, it works out to be 2 pi times the integral from -1 to 1 of mu d mu, which is an easy integral to do and gives 0. So the cos theta integral gives 0, which makes sense if you think about it, because cosine theta spends as much time being positive between 0 and pi over 2 times spends as much, something, angle, whatever, being, I'm blue, being positive between 0 and pi over 2 as it does between being negative between pi over 2 and pi, and so it all cancels out when you do the cos theta integral. So that gives you 0. So what do we get? Put it together, and what do you got? Bibbidi bobbidi, right, or whatever, right? It's, what is that? Is that Mary Poppins? What is that from? Like, you even know what I'm talking about. You're just, yeah. What is that from? Is that? Is it what? Cinderella. Oh yeah, Cinderella. That's right, Cinderella. Yeah. Well, make the lovely dress for Cinderella. Right. Okay. So I gotta know my Disney better, right? Where was I? So we get that the P rad, d tau v, is 1 over c times f rad, because I didn't put that there, but the I cos theta d omega we did before, and that was f rad. So this is another important equation that therefore gets a box and a number. Guess I'll add that to the collection over here. And we said, oh, this is f rad. Right there again, if it showed up again, because it was there before. Only this time it showed up on the right side, whereas before there was already a cosine theta on the left side. Yes?
What's FCV?
This is the speed of light times the radiation pressure. Is that what you're asking?
Yes.
Yeah. That's the speed of light times the radiation pressure. Yeah. So that's it. From earlier, a while back, we did these, moments of the radiation field, and blah, 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 and C times the radiation pressure is that number right there. So at this point, it's like, take my word for it, but, it's, you don't even have to actually see it. But we're not going back there right now. Yes. Okay. So if we want to give this an interpretation, we can. This can be interpreted somewhat fancifully, to be honest. I'll even interpret it somewhat fancifully. As saying that a breeze of photons, so to speak, a breeze of photons. Okay. Well, it's like outside now, it's breezy, right? So now we're having a breeze of photons flows outward in response to the radiation pressure gradient. One thing I should remind you of that you might have forgotten is that F rad is the net flux of radiation. So if the radiation is isotropic, the same in every direction, what is F rad equal to? If the radiation is isotropic, the same in every direction, F rad is the net flux of radiation. It's the upward flux minus the downward flux, because photons are going in every direction, so you might have more going out than going in, you might have more going in than going out in principle. If the radiation field is isotropic, the same in every direction, then, based on what I've said, what should F rad be in that case? It should be 0, because there will be just as much flux flowing upwards as flowing downwards. So, in other words, in an isotropic field, dp rad d tau v would be 0. The radiation flux would be 0 in that case. So if there's no radiation pressure gradient, it's not changing with position, it'll be no net radiation flux either in that situation. So be sure you realize F rad isn't the outward flux or the inward flux. It's the difference between the outward flux, watts per square meter flowing outwards, and the inward flux, watts per square meter flowing inwards. Question?
Is that word response?
It's response, but it's supposed to be response. Yes, thank you. In response is French. It's not French, but I'm making it up that it's French. No. Yes.
That's dirty letter.
There we go. Okay, so now we're going to make the plane parallel approximation again, meaning we better be sticking to some small region of the star. Let's be in the star's atmosphere, okay? The technical description is sun, right? And so if we look at some small region near the sun's surface, it's a decent approximation to say everything is layered horizontally, even though we know the sun is actually a big, giant curved sphere. It's a big, giant curved sphere, and so any small region we can approximate as plane parallel approximation to the atmosphere. And so in a stellar atmosphere in equilibrium, in a stellar atmosphere in equilibrium, meaning things are not changing with time, they can be changing with position, but not changing with time, in a stellar atmosphere in equilibrium, if it can be approximated as plane parallel, and we can just think of it as horizontal layers. So our picture would be like, okay, it's really just continuous, but imagine that in our minds or in our computer or whatever, we think of a bunch of layers in the atmosphere. Oh, look at those beautiful layers. It's like a layer cake. Looks delicious, doesn't it? If we can approximate it as, and here's the surface of the star, the mythical surface, because it really just fades away. If we can approximate it as plane parallel, then F rad at every level, F rad at every level must be equal to the value at the surface. And I'll keep writing and then we'll say why. In order that for each layer, the energy flowing in from the bottom equals the energy flowing out at the top. I'll say the net energy, because again, photons are moving every which way, but there can be a net. There can be more flowing out than flowing in. That what has to happen in a star is there has to be more radiation flowing out than in, because stuff's got to escape from the surface. In order for in each layer, in each layer, so that's an in there, but that's an in right there. That's more than because you're going to ask. I didn't read that. I was just waiting for you to say, wait, what's that? In order that, in order that in each layer, let's get rid of one. In order that in each layer, the net energy flowing in from the bottom, flowing into the layer from the bottom, I have to read my thing so far. In order that in each layer, the net energy flowing into the layer from the bottom equals the net energy flowing out of the layer from the top. So why should this be? I'm about to, okay. What's illegible?
No, I
Are you just trying to soak it all in?
didn't remember it.
Okay, let's see. Let me read it and see if I'm confused. In a stellar atmospheric equilibrium, if it can be approximated as parallel, then F rad at every level must be equal to the value at the surface in order that in each layer, the net energy flowing into the layer from the bottom equals the net energy flowing out of the layer from the top. I'm actually happy with it.
It makes more sense.
After I read the whole thing, yeah. Right, okay. So in other words, the idea is in every layer, there's energy flowing into the layer from the bottom. There's energy flowing out of the layer from the bottom. But there better need to be more flowing out than in, so that there's a net outward flow of radiation. Now at the top, and that outward flow is into this layer right here, right? Here's focus on this layer. I could draw this for all the layers, but let's focus on that layer right there. Right? So there's a net flow into it from the bottom. There's a net flow out of it from the top, because again, there's more radiation flowing out than flowing in, and then my arrows are just, I'm supposed to be illustrative. Don't take them too literally. It's like radiation flowing out, radiation flowing in. Just kind of like longer arrow speed, more flowing out than flowing in. So if we're to be in equilibrium, well, what would happen if more energy was flowing into this layer from the bottom than was flowing out from the top? What would happen to, say, the temperature of the layer if more energy was flowing in than flowing out? What would happen to its temperature? It would increase. But we're in equilibrium, so should the temperature be changing? No, it should not. Equilibrium means things aren't changing. So, at least with time. Different layers will have different temperatures. There's change with position, but each layer's temperature should stay constant. That's the equilibrium condition here. Okay? So, here's the thing. At the surface, I've got energy flowing out at the surface. Is there any energy flowing in at the surface? If you're at the surface, well, if you're down here, if you look up, you go, ah, it's so bright! And if you look down, you go, ah, it's so bright! Right? In fact, you go, ah, it's so bright! Ah, it's so bright, because there's more flowing up than flowing down. But if you're at the surface, if you look down, you go, ah, it's so bright! And if you look up, what do you see? Darkness, it's space. What's that? That's right. You know, it's time to talk with you again. I had a vision, so anyway, so, all right. At the surface, there's only energy flowing out. Okay, there's starlight, right? Essentially, there's only energy flowing out. There's no energy flowing in. And that's the whole point of this, right? You kind of think layer by layer here. At the surface, there's a net energy flowing out. There's a surface flux. And the net flux down here better be the same. In order for everything to stay in equilibrium, this flux, the net flux in, the upward flux minus the downward flux, it better be equal to the surface flux, because otherwise this layer would be heating up or cooling down. Does that make sense? If there's more energy flowing in than out, or vice versa, the temperature of the layer would stay the same. So however much energy per square meter per second is flowing out of the surface itself, the net energy per square meter per second flowing into the bottom of this layer has to equal the surface flux. The surface flux is only outwards. But wait, I can make the same argument here. The energy, the net flux here is the surface flux. But that means this also has to be the surface flux for this layer to be in equilibrium. But then this layer also has the net at the bottom surface flux, surface flux, surface flux. So in other words, the flux just has to be constant all the way down and equal to the flux at the surface. Otherwise, we would not be in equilibrium. That's the content of this beautifully constructed, highly grammatical sentence. That's the point that we're making there. It's a powerful argument. Thus, at every depth, no matter where you are, at every depth, the radiative flux, which again is the net outward flux. It could be inward, but in the star it's outwards. The net radiative flux, F rad, is equal to a constant. Otherwise, we would not be in equilibrium. Layers would be heating up or cooling down. The radiative flux is a constant. And remember that by definition, that constant is sigma Tef to the fourth power. The effective temperature, right? Because the effective temperature is the thing which makes the actual flux sigma Tef to the fourth power. So by definition, that's sigma Tef to the fourth power. So I can even make this a glorious triple equals. By definition, that's sigma Tef to the fourth power. Okay, you buy that? Let's continue selling you things then. So, since F rad is constant, that says dF rad d tau b is equal to 0. Right? The derivative of a constant is 0. If you don't know that, go back to calculus. Since dF rad d tau b is 0, we have that the mean intensity is equal to S from equation 1, because equation 1 said the derivative of the radiative flux is mean intensity minus S times 4 pi. So if it's 0, the mean intensity is equal to the source function. That doesn't mean the intensity is constant. It means its average over solid angle is constant, because it's not constant. The intensity is higher upwards than downwards, because we need to have more energy coming out than coming in. And glorious equation 2 implies after integrating with respect to tau v, right, so let's write 2 again was dp rad d tau v is equal to 1 over c f rad, okay? But f rad is a constant, so let's integrate both sides. dp rad d tau v is 1 over c f rad. Integrate with respect to tau v, because f rad is constant. Get to pull it out of the integral. What's what's the integral of the derivative? The function, right? The function itself. So I can say, right, the integral of the derivative of f is f, right? The integral of the derivative of dp rad is p rad. Radical, man. So that says p rad is equal to 1 over c f rad times tau v, because the integral of d tau v is tau v. And I could do this as a definite integral, or I could do this as an indefinite integral and add c, a constant of integration. Not the speed of light, so maybe I'll give it a hook there and say that ain't the speed of light. Constant of integration. Maybe I shouldn't call it A. It's too late now. There's no way I can erase this. Constant of integration. So notice this says that the pressure increases with optical depth. That makes sense. This pressure should be rising as you go deeper inside the atmosphere. Now, we're going to make the famous, in astrophysics circles at least, Eddington approximation after Sir Arthur, as his friends called him, Sir Arthur Stanley Eddington. Knight of the Realm for his contributions to astrophysics. Now we make the Eddington approximation. Remember we talked about the Eddington limit before for stars and stuff like that. Turns out he was a very talented astrophysicist, theoretical astrophysicist. Now we make the Eddington approximation. And I'm going to show a figure that illustrates the idea after I log in here. A figure from your book that illustrates the idea. I forget what times already. Okay, so and even if it had showed up there, this time it was all dots. Change my password. And then this will help if I get over here. The Eddington approximation. What? Oh, with respect to. With respect to. Which? Yeah, which? With respect to. Yes. Sorry. I just assumed that, you know. So by the way, if you come to my office and I have my whiteboard, it says BRB. What does that mean? You write that. Okay, just checking. I just want everybody to go up there and say burr.
Send you an email.
Yeah. I have heard people use burb to stand for bird. Like I have friends who like birds a lot, and I was just he'd post things like, "Oh, look, it's a cute burb." So, what's that? Yeah, just put a burb. Yeah, that's right.
Only the ones who know.
That's right. F is an L, and then we'll draw a wild boar next to it. I'm not sure where she got the wild boar thing, but there we are. I appreciate it. So now we make the Eddington approximation. And here's the illustration. So really the specific intensity varies smoothly with angle away from the vertical. But to make the calculation simpler, Eddington said, okay, you know, I'm a astrophysicist, spherical cows and all that, right? You know about spherical cows, right? Let's make the hemispherical specific intensity approximation, where it's a constant in all outward directions and another constant in all inward directions. with the constant outward in specific intensity being bigger than the constant inward one, because there has to be a net flow outward of radiation. So the Eddington approximation is I out equals constant, right, between theta equals 0 and theta and pi over 2, and I in equals a different and smaller constant. To make the calculations tractable, you know that word tractable? When it comes to like calculations, if something, or problems, a problem is tractable if it's possible to solve it. And a problem is intractable if it's not possible to solve it, or at least it's super difficult to solve it. Okay? So, in this case, see the glorious homework, although it's not difficult. And it hasn't been posted yet, so this is a see the future glorious homework. Thank God. I believe you mean, oh damn. I wanted to do that this evening. See the glorious homework. In this case, I mean, I'm going to have you show this by doing the integral, but because you're going to integrate over solid angle to find the mean intensity, for example. But what else could it be than literally the average of I out and I in? Half of I out plus I in. Gosh, that seems to make sense. F rad is, so you may remember for black body radiation, F lambda is what times B lambda? I times B lambda, and this is true for any isotropic radiation field. So we can also say F lambda is pi I lambda if I lambda is isotropic. I should say F lambda in the outward direction, right? This has to be just this is the one-sided flux here. So I don't have to, F lambda is understood to be the one-sided flux, either the up flux or the down flux here. It's not the net flux when I do it this way. Okay, so is I out isotropic as far as it goes? It is, right? The overall radiation field is an isotropic, it's bigger up than down, but the outward flux, that relation comes from doing the outward flux or the inward flux. So, in other words, as long as my radiation is isotropic over a hemisphere, then F in that direction is going to be pi times the specific intensity in the outward or the inward hemisphere. In other words, F rad should be and is pi times I out, but wait a minute, F rad here is the net radiative flux. So should it be I out plus I in or I out minus I in here? It's the net flux. It's going to be minus. It's going to be minus because, in other words, pi I out is how much there is of outward flux. Pi I in is how much there is of inward flux. And the difference between them is the net flux in the outward direction. So it will be, in fact, minus pi I out minus I in. And again, I'm just saying, well, this, kind of arguing, well, this is what would make sense. And you'll actually do the integral and it'll be like, yeah, that's exactly what it came out to. Just to be sure that you're kind of following. And then finally, the radiation pressure is 2 pi over 3c times I out plus I in, which is 4 pi over 3c times the mean intensity. And indeed, if you have an isotropic radiation field, then the radiation pressure is 4 pi over 3c times the constant intensity. But here, because it's constant up and another constant down, it breaks apart into two pieces, each of which gives 2 pi over 3c. If I out and In were equal to one another, if it was isotropic, then indeed we'd have P rad as 4 pi over 3c times I in that case, if it were isotropic, which is what you get for an isotropic radiation field. But since there's an outward piece and an inwards piece, each contributes 2 pi over 3c times that value. So that's what the radiation pressure looks like. Questions, comments, observations? So now we get another thus, and it's like, wait, what's it from? Yeah, I gotta remind myself here. Yeah, the thus is gonna come, remember we said that P rad was equal to, I'm just reminding, is it already there? P rad was 1 over C F rad tau V plus constant. This plus, isn't it? So little chalk left, but also so little time. I feel like I should milk this little stump all the way here. You can do it, little chalk. Come on, you can do it. Thus, this plus those three beautiful equations give that 4 pi over 3c times the mean intensity, right, that's the P rad, is equal to 1 over C F rad tau V plus constant. Actually, it's plus, okay, one of those beautiful equations, because it's just one of them. I was getting over optimistic there. So this is equation 3. That's equation 3. And again, right, it's like, where is this going? And I remind you, no. We're walking through an enchanted forest here. We're going to open a little cabin, and little elves are going to come out and say something really cool. Okay, so, all right. So, at the top of the atmosphere, tau V is equal to 0 because there hasn't been any absorption yet. I remember that we're looking into the atmosphere and we're at tau V equals 0, and it stays 0 until you get to the atmosphere because there hasn't been any absorption yet. So d tau equals minus kappa rho ds is 0 if rho is 0 between you and the point in question. So tau V, the vertical opposite vector, is 0 at the top of the atmosphere. And if we, did I actually move the camera or not? Maybe the audience at home hasn't seen what I wrote on that board over there. No, here it is. There it is. There's that. Of course, you were just, you were looking at my notes or just like writing down what I said, or saying, finally you turned the camera, Dr. Harmon. Any of those things is possible. So there it is, right? There it is, okay? At the top of the atmosphere, tau V, the mercury molecule depth is equal to 0. Did you have a question? There we go. Okay. The mercury molecule depth is 0, and In equals what? At the top of the atmosphere, what's the inward specific intensity? I'm at the top of the atmosphere, I look up, what do I see? I see space, the final frontier. So In is 0 up there, except for starlight. Who cares about the starlight? It's nothing. Okay. This is the star alone in the universe, or starlight's a lot dimmer than the star's own radiation. So In is equal to 0. So at this location, right, so in the Eddington approximation, realize, right, spoiler alert, the idea is you go deeper and deeper down, In and I out both increase. They maintain a difference from one another, but they're both increasing, because as you go down, it's like, oh, now if I look up, there is radiation coming down towards me, right? But at the surface, black sky, okay? So as you go down, both of those are getting bigger. So, at the top of the atmosphere, tau V is equal to 0, In is equal to 0. So at this location, not this location, the mean intensity is just half of I out, because In is 0. And F rad is pi I out, because In is 0. And so we can say that the mean intensity, and also, anyway, the mean intensity evaluated at tau V equals 0 at the surface is equal to F rad over 2 pi. That constant net radiated flux divided by 2 pi. Because it's obvious to me in my notes here. Yeah, so the mean intensity is half of I out, but that says that it's 1 over 2 pi times F rad, just combining these two things with one. So the mean intensity at the surface is the radiated flux divided by 2 pi. Okay, so now what? What excitement happens here? Right, this is a simple 74-step process getting here. Setting tau sub V equals 0 in equation 3 over there yields that 4 pi over 3c F rad over 2 pi is equal to that constant of integration. All right, so I evaluated tau V is equal to 0, and so this term goes away, and so you get 4 pi over 3c times mean intensity of tau V equals 0, but that's F rad over 2 pi. So I plug all that into that equation, and I've evaluated the constant of integration. First, we had the unknown constant of integration. Well, now we know it. Now we know it. So this says that the constant of integration is 2 over 3c times the radiated flux. 2 over 3c times that net constant radiated flux. So the elves are about to appear. So 3 becomes 4 pi over 3 times the mean intensity is equal to F rad times tau v plus 2/3. And, oh, remember something about like optical depth of 2/3 and stuff like that. Starting to show up here. I plug it, right? So what I did here is I plugged in that C here was equal to 2 F rad over 3C. Right? Which is terrible, because that's why I better have a hook here, because this is a capital C, that's the speed of light. Okay? So just to be clear. So that's a snake, right? That's a, okay, that's a serpent spelled with a C. So, right, this was 2 over 3C. I'm really running out of chalk here. We're going to do this 2 over 3C F rad. So I plug that in there, and that gives me then 4 pi over 3, because I can cancel all the C's that are every term now, is equal to F rad times tau v plus 2/3. Does it make sense? It's a factor, like not buying it ourselves.
So there's a C, functional integration,
Yep.
and then we plug that in.
Plug this in here, yeah, so that F, so the front to capital C was this, right? So then now I've got a C in every term, 1 over C, 1 over C, 1 over C. So I can cancel all the constant speed, I can cancel the speed of light, so 4 pi over 3 mean intensity is F rad, stop it, F rad plus 2/3 F rad tau v plus 2/3 F rad, which I factor as F rad times tau v plus 2/3. So that's the logic there. Very easily read, as you can see, right? Yes. Because I have so little, I feel like, just it's going to be a mark of pride if I can, I should have done that, make this tiny little stump of chalk, make it to the end here. So efficient in my use of resources. Where are we at? I'm going to give you some free education. I just have to, because it's just waiting 5 days to see this again. You're like, what? You might be like, what? Now the end of the what? Okay? We don't want what? All right, so free education, because we're so close. Using F rad is sigma F to the fourth. We have that the mean intensity is, okay, replace F rad in that equation I just erased with sigma F to the fourth, 3 sigma over 4 pi F to the fourth times tau v plus 2/3. So I just replaced F rad with sigma F to the fourth in that prior equation that I just wrote. Oh, so little to go. We're almost there. Assuming LTE, which of course stands for local thermodynamic equilibrium, right? We have, oh, this is getting hard to do. We have the mean intensity is equal to the source function from 1, something we said before, that in LTE, the mean intensity is equal to the source function in order to make that derivative 0. And we also said S lambda is equal to B lambda. in LTE, because in thermal equilibrium, S lambda is equal to B lambda, 2, 4, 6, 8. Let's integrate them both. So S, which is the integral of S lambda d lambda, which we did that, right? S lambda d lambda, well, that'll be equal to the integral of B lambda d lambda. But we know what the integral of B lambda d lambda is. What's the integral of B lambda over all wavelengths? What's the integral of F lambda over all wavelengths? That's the Stefan-Boltzmann equation. So if integrate F lambda over all wavelengths, I get sigma t to the fourth, but F lambda is pi B lambda. So when I integrate B lambda over all wavelengths, I get sigma t to the fourth over pi, sigma t to the fourth over pi, and thus, I don't know why I'm insisting that, okay, I have to get off. So, well, I did use all the chalk, so it's morally equivalent. Okay. And thus, here comes the elves, or the gnomes, or whatever. Apparently, people in Iceland actually leave food out for like I think it's the elves in the countryside, elves or gnomes, I can't remember. But apparently, a lot of people in Iceland actually think there's like gnomes or elves living in the hillside or something like that. Kind of cute. In other news, no. And thus, what we get out of all this is the glorious t to the fourth is equal to 3/4 f to the fourth times tau sub b plus 2/3. In other words, what am I trying to say here? Yeah, I is equal to S, and S is sigma t to the fourth over pi. So over here we would put sigma t to the fourth over pi. Right? Sigma t to the fourth over pi is 3 sigma over 4 pi tef to the fourth, tau b plus 2/3. So now or divide through by sigma over pi, it cancels on both sides. And so we get t to the fourth is 3/4 tef to the fourth, tau b plus 2/3. Why is this glorious? Why is this elves? Elves appear. Elves appear. This is where we've been headed. Elves appear. This is for a gray atmosphere. Eddington approximation, LTE. Have to put down what went into this. Eddington approximation, LTE. Okay, we'll revisit this next time. But what it says is that the actual temperature of the layer at an optical depth tau v equals 2/3 is equal to the effective temperature tef. Right? Because if I plug tau v equals 2/3 into this, I get 4/3 in the parentheses, multiplied by 3/4 says t equals tef, where tau v equals 2/3. And this is the sense that we see to an optical depth of 2/3 that we talked about. In other words, the radiation we see looks like the radiation coming from the layer at an optical depth of 2/3. What we really see is radiation right into the sun. The sun doesn't have a solid surface, it's a gas. we see radiation coming from many, many layers as we look deeper and deeper in. It's a blend that all works out to this effective temperature, TEF, and that effective temperature that that blend of radiation appears to have is the actual temperature of the layer where the optical depth is 2/3. So in that sense, when we look at the sun, it looks like the radiation coming from an optical depth of 2/3 below the surface. We'll explore that more further later. It's more than time to go. I gave you this wonderful, well, I gave you free education. I don't know if you, it's wonderful! The elves came out. See you next time. See you before next time. Yeah. I have my office hours now in case you have anything you'd like to talk about.